So we need to know a few basic facts. First of all, there are 3 metals which are ferromagnetic, which means permanent magnets. So there are 3 metals that are always magnets, no matter what time of the day it is, no matter where they are, what they're doing. Okay, these are iron, nickel, and cobalt. Right, they're 3 special metals. Nothing else is a permanent magnet. It doesn't mean we can't turn it into a magnet, but nothing else is a permanent magnet. Okay. Now, you might have heard of neodymium magnets. Which are compounds, and you obviously know what compounds are, or I could say alloys. So they are a mixture of metals. I'm not going to go into detail about what these are made of, but they are a mixture of metals. These are metals on their own that are ferromagnetic.
So can you move your work to the side? So
this way?
Yeah.
Yeah, so for some reason, what you see on your screen doesn't match up to what I see. So just, let me know. Okay, so we now have permanent magnets, which are always magnets, and we have induced magnets, which are basically temporary magnets. So there is a difference here. So for things that are always magnets, right, this is what you're used to seeing when you look at a magnet, right? So if you've got some fridge magnets, these are permanent magnets. So you have a magnet with a north pole and a south pole, and you can draw on some magnetic field lines. And you've probably seen this diagram many, many times. All right. So you need to be able to draw this. You need to be able to draw it neatly. Do 5 lines is enough. If you do 10 lines, too many lines. Okay, 5 lines. You need to do the arrows, and the arrows need to go north to south. All right, that's the convention. And what do the lines show? They show the force. So a force that another magnet would feel. And this is stating the obvious. If you have a north pole and a south pole, opposites attract. If you have a north and a north, they repel. And if you have a south and a south, they repel. If we look at induced magnets, these are temporary magnets. So they sometimes exist, sometimes don't. Okay, so an example is an iron nail. Okay, so an iron nail, right, on its own is not magnetic. However, if you put an iron nail near to a magnet, then it becomes attracted. And it's always attracted to the magnet. Okay, and then what you can do is you can then use it as a temporary magnet to attract other nails. All right, but if you remove this, what's going to happen? They're all going to fall off. It won't be a magnet anymore. So if you remove this magnet, it won't be magnetic anymore. That's why it's an induced magnet. Induced means you make or create. So one classic question which catches people out because it's so easy is how can we show what the magnetic field looks like? So if we have a magnet, how can we show what this field is? So we know what it looks like, but how can we show what it looks like? So there's two ways to do it. One is you can use compasses or plotting compasses if you want to sound fancy. So a compass, as I'm sure you will know, right, is just a thing that will point north. It's a little mini magnet. So you put a little compass here and the arrow points to the north. You can then put another compass and it will show you the field line. If you put a compass over here, it will show you where north is, so it'll point the other way. Okay, if you put a compass over here, it will show where north is. So it'll show where north is and point towards north. Or you can use iron filings. All right, what iron filings do, well, iron is a temporary magnet, it's induced, so it will be attracted to the magnet, and so you will see the pattern. I'm just going to briefly show my screen, and then I'll go back to the visualizer. So you've probably seen this image on the PowerPoint. Hopefully you can see the PowerPoint. All right, this is a magnet, and around it you've got loads of iron filings that have been sprinkled on the paper. And the iron filings line up on the magnetic field lines, and you can see the pattern. All right, and it's quite amazing, really. It's quite pretty. You can see the pattern. Right, so a couple of other little things that relate to this. Right, we know that if you have a North Pole and a North Pole, you know that they're going to repel. What do the magnetic field lines look like? Well, the field lines repel each other, so they don't want to go anywhere near each other, right, because they're repelling. So what do? They bend away and they try and get away from each other. All right. And in the middle here, there is no force. All right, the forces are balanced. If we have a South Pole and a North Pole like this, and this will become really important when we look at some lessons after half term. Right, what do they do? They obviously attract. So what do the field lines do? Well, they attract each other, and they do actually join up, and the arrows always go north to south. And then, as I'm sure you all know, especially if you do geography, right, this is the Earth with some random countries in. The Earth has a magnetic field. right, which is really useful because we can then navigate. All right, how do people on ships navigate? If you're doing Duke of Edinburgh, how do you find your way around? Right, you use the compass, right, and the compass always points north to the North Pole. So there is a magnet inside the Earth. Right. Why is that magnet there? Right, the core is iron. The iron inside the Earth is magnetic, and that makes these field lines here. Right, are there any questions so far? All right, super quick quiz, and then I'm going to get you doing some questions. So you should be able to see a PowerPoint. It has 5 questions on it. 1 minute. Are they true or false? Okay, question 1 is false. They don't always attract each other. Question 2, false. Question 3, true. I didn't say that, but hopefully that's obvious. Number 4 is true. And number 5 is false. It does tell you the direction of the field. Excellent, Ishra.